Welcome, future aviators, to a deep dive that's going to really fast-track your understanding of one of the most iconic training aircraft out there, the Cessna 172S.
That's right.
If you're studying for your check ride, maybe prepping for a flight, or just fascinated by how these incredible machines actually work, you've definitely landed in the perfect place. Today, we're not just flipping through pages. We're actually cracking open the pilot's operating handbook, specifically Section 7, Airplane and Systems Description, and some key supporting sections, too.
Yeah, the real source material.
Exactly. We want to extract the most vital nuggets of knowledge about the heart and soul of the Skyhawk. This isn't just going to be a list of parts.
No way.
It's about understanding how everything works together, what you need to look for, and importantly, why every detail matters to you when you're sitting in that cockpit.
And that's precisely our mission today.
Right.
To take all that sometimes dense manual data and turn it into actionable insights, things you can actually use. We want to help you build a mental model of the 172S that's not just thorough, but feels, well, intuitive.
Makes sense.
We're going to cover pretty much everything, from the basic structure holding it together, all the way to the intricate electrical network powering your flight.
Yeah.
Our goal is to ensure you gain a quick, yet really comprehensive grasp of the aircraft's fundamental systems. Think of this deep dive as your shortcut to truly knowing your airplane, not just memorizing facts for the test.
Love that. Knowing versus memorizing.
Exactly. We're diving beyond the what and getting into the why for every new pilot out there.
Okay, let's get into it. Let's unpack this by starting with the very foundation. Before we even think about turning a key, right? We need to understand what this machine is actually made of, how it's put together.
Yeah, the basics.
So let's talk about the overall construction and maybe the design philosophy behind the Cessna 172S. What's the big picture?
Well, at its core, the Cessna 172S is engineered for reliability and straightforward operation. That's a big reason it's such a staple in flight training, right? The whole design philosophy centers on being robust, easy to maintain, and that directly benefits you as the pilot. So let's look at the empennage first. That's just the fancy aviation term for the tail assembly.
Got it. The tail.
Yeah, the tail. It's a conventional design. That means it has a vertical stabilizer and a rudder for directional control, keeping the nose straight, and a horizontal stabilizer and an elevator for pitch control, making the nose go up or down. Pretty standard setup.
So when we talk about how they're actually built, what's the most important takeaway for a new pilot? Are we talking rivets and sheet metal details, or is it more about the functional design?
That's a really good question. It gets to the heart of what's practical for you, the pilot, to know. While, yeah, it's good to know that components like the vertical stabilizer are built with the main spar. Think of it like the backbone, right?
Yep.
And formed ribs, kind of like the frame of a bicycle wheel. But what's really critical for you to remember are the design elements that directly impact flight safety and control. Like, for instance, the rudder. It has a leading edge extension, sort of sticks out a bit at the top front, and that contains a balance weight.
Okay.
And the elevator also has these balance weights located in its tip leading edge extensions.
Wait, balance weights. That we find on a car tire. Why are those so important on a control surface? What happens if, say, one gets damaged during pre-flight?
Exactly like on a car tire.
Yeah.
But with potentially much more serious consequences in the air, these balance weights are absolutely vital. Vital for preventing something called flutter.
Flutter. Sounds bad.
It is. It's an uncontrolled high-frequency oscillation or vibration of the control surface. Imagine it starting to flap violently, like a flag in a hurricane. It can lead to structural failure incredibly quickly.
Wow. Yeah.
So these weights make sure the control surfaces remain aerodynamically balanced. They ensure smooth, predictable control responses. So during your pre-flight, if you see any damage in those areas, a dent, maybe a piece missing, anything that looks off that's not just cosmetic damage,
Right.
that's an immediate grounding item because it compromises a critical safety feature. It directly informs your pre-flight inspection, helping you understand why the airplane feels stable and responsive in flight.
That makes perfect sense. It's not about memorizing every single part number, but understanding the function and the why behind the design.
Precisely.
Right? So we know what the pieces are, why they're built that way.
Yeah.
Now, how do we make them move? Let's unpack the flight control system. This is where the pilot really connects with the aircraft, right?
Exactly. And the flight controls in the 172S are, well, wonderfully straightforward. They are all mechanically linked. That means cables and push rods.
So a direct connection.
A direct, reliable connection between your inputs and the aircraft's response. When you move the control wheel, or the yoke, as most people call it,
Yep.
you're directly moving the ailerons for roll that's banking left or right, and the elevator for pitch, making the nose go up or down. Then your rudder pedals. They control yaw, which is the side-to-side movement of the nose. And importantly, they're also your primary tool for nose wheel steering when you're on the ground.
Ah, yes, ground control.
Yeah.
I remember learning to taxi felt like a bit of an art form initially. How do the rudder pedals actually connect to the nose wheel?
Good point. It's actually pretty clever. On the ground, those rudder pedals are connected to the nose wheel through a spring-loaded steering bungee.
A bungee.
Yeah, basically. It allows you to turn the nose wheel about 10 degrees each side of center just by pushing a rudder pedal. Nice and simple for taxiing straight or making gentle turns.
Okay, 10 degrees. What if you need a tighter turn?
Right. If you need to maneuver in a crowded ramp area or make a sharper turn, applying the brake on one side, the main wheel brake, will increase that turn angle significantly, up to about 30 degrees each side.
Ah, differential brake.
Exactly. It's a simple, effective system that gives you pretty precise control during taxi.
Now, here's something that always stuck with me, and I think it's crucial for new pilots. The control locks. I remember instructors being really insistent about them. Why are they so important? What are they actually preventing?
Fantastic point, because it's a small, simple device with huge safety implications. The Pilot's Operating Handbook, the POH, specifically talks about a control lock. It's usually just a shaped steel rod, often with a bright red or orange flag attached.
Right, the flag.
Its main job, to lock the aileron and elevator control surfaces when the plane is parked. Why? To prevent wind damage.
Ah, makes sense.
Imagine the airplane sitting on the ramp on a windy day. Without that lock, those big control surfaces would get blown around, maybe slamming back and forth violently.
Yeah, I can picture that.
That buffeting could cause serious damage to the hinges, the internal linkages, even the structure itself. And that flag isn't just for show.
No.
It's designed usually to cover the ignition switch. It's a physical barrier. It basically screams at you, don't even think about starting this engine until you remove me.
A critical reminder.
Absolutely. And for really high or gusty winds, the POH even recommends using an additional external lock that goes over the vertical stabilizer and rudder for extra protection. So remembering to put it in when you leave the aircraft, and this is critical, remembering to take it out before starting, is a fundamental safety procedure. It protects your aircraft from potentially very expensive and dangerous damage.
Got it. Install and remove. Simple, but vital. Okay, beyond the primary controls, ailerons, elevator, rudder, we have flaps. Essential for generating extra lift and drag, right?
Mm-hmm.
Especially during takeoff and landing. Tell us about the 172S's wing flap system.
Right. The Cessna 172S has single-slot type wing flaps. These are pretty common. Their extension or retraction is controlled electrically using a switch lever on the instrument panel.
So it's an electric switch, not a big manual lever like in some older planes.
Correct. You'll see the switch lever moves within a slotted panel right there on the dash. And it has very clear mechanical stops or detents at the 10, 20, and 30-degree positions.
Now you select those positions.
To change the flap setting, you actually push the lever slightly to the right to get it out of the detent. Then you slide it up or down to the position you want. It then clicks back into place.
Okay.
And right next to the switch, there's a little scale and a pointer that shows you the flap travel in degrees, so you get positive confirmation of the setting.
Since it's electric, is there circuit protection?
Yes, absolutely. That system is protected by a 10-ampere circuit breaker. It's clearly labeled FLAP, and you'll find it on the left side of the main control panel, usually near the other breakers.
Good to know where that is.
It highlights that important principle again. Even systems that seem straightforward often have underlying electrical components, and crucially, some form of protection, like a circuit breaker. Knowing this helps if you ever need to troubleshoot, like if your flaps aren't moving, first check the breaker.
Makes sense. All right, let's bring it back down to earth, literally. What's the deal with the landing gear system on the 172S? It always seemed pretty robust to me.
It is pretty robust. The 172S uses a tricycle-type landing gear configuration. That just means it has the steerable nose wheel up front and the two main wheels further back arranged in a triangle.
Like most modern trainers.
Exactly. It provides excellent stability during ground operations, takeoff, landing, taxiing. It's much easier to handle on the ground than older tailwheel aircraft. And for better aerodynamics and a bit of protection from, rocks and debris, wheel fairings, or wheel pants, as some call them, are standard on all three wheels.
Okay. How does it handle bumps and the impact of landing?
There's actually a subtle but important difference between the main gear and the nose gear. The main landing gear struts are made of tubular spring steel. They basically absorb shocks just by flexing. Simple, strong, very little maintenance.
Right, I've seen those bend a bit on landing.
Exactly. The nose gear, however, is different. It uses an air oil shock strut. Think of it like a shock absorber on a mountain bike or a car. It uses compressed air and hydraulic fluid to provide damped absorption. That means it compresses and extends in a more controlled manner. This gives a smoother response to bumps and landings, which is especially crucial for the nose wheel since it takes a lot of stress, particularly if you land a bit hard on it.
And brakes.
Brakes are on the main wheels only. Each main gear wheel has a hydraulically actuated disc-type brake mounted on the inboard side. These are connected via hydraulic lines to master cylinders attached to the top of your rudder pedals.
So, toe brake.
Correct. Pushing the top of the rudder pedals activates the brakes. This allows for individual wheel braking, differential braking, which is essential for steering assistance on the ground, especially in those tighter turns we mentioned. And of course, pressing both together provides main braking for stopping. There's usually a parking brake handle, too, to lock the pressure in the system.
Right, that covers the airframe and landing gear, the skeleton and feet, if you will.
Good analogy.
Now for the heart of the beast, the engine. Give us the lowdown on what powers the 172S.
Okay, the engine. The 172S is powered by a Textron Lycoming model IO360 L2A engine. Let's break that down a bit.
Please do. IO360 L2A sounds like a code.
It kind of is. IO means it's fuel injected. OA means it's horizontally injected. Opposed, the cylinders lie flat, opposing each other. 360 refers to the engine displacement in cubic inches, roughly. And L2A is the specific model variant.
Got it. So fuel injected, horizontally opposed, 360 cubic inches. What else?
It's a 4-cylinder engine, uses overhead valve like most modern car engines. It's air-cooled, no radiator, just airflow over cooling fins, and it has a wet sump lubrication system.
Wet sump means the oil's stored in the bottom of the engine, right? Not a separate tank.
Exactly. The oil pan at the bottom holds the oil. This engine is rated to produce 180 brake horsepower, bhp, at 2,700 RPM. It's a very reliable, well-understood engine, common in general aviation.
And that fuel injection, that means no carburetor icing worries, right? That's a big plus compared to some other trainers.
That's a major operational advantage, yes. Fuel injection delivers fuel more precisely right near the cylinder intake, generally avoiding the conditions where carburetor ice can form.
Okay. What about the key accessories on this engine? What keeps it running?
Right. Besides the core engine, there are several critical accessories. If you look at the front of the engine, you'll see the starter motor and the belt-driven alternator, which generates electricity for the aircraft systems and charges the battery.
Standard stuff.
Pretty standard. But what's really important, especially for safety and something new pilots should definitely grasp, is the redundancy built into the systems mounted at the rear of the engine on the accessory case.
Redundancy sounds good. What systems are duplicated?
You've got dual magnetos and dual vacuum pumps.
Dual systems. Okay, that sounds like a big deal. Why 2 of each? What's the implication?
It's a huge deal for safety and reliability. The dual magnetos mean you have 2 completely independent ignition systems. Each magneto powers 1 spark plug in each cylinder, so 2 plugs per cylinder total.
Ah, so if one magneto fails.
If one magneto fails, the other one keeps the engine running. You might notice a slight drop in RPM during your pre-flight magneto check, but the engine continues to operate safely. This redundancy ensures a more complete burning of the fuel-air mixture and provides a critical layer of safety.
Okay, that makes sense for ignition. What about the dual vacuum pumps?
Similar principle. The vacuum system powers some of your key gyroscopic flight instruments, typically the attitude indicator, your artificial horizon, and the directional indicator, heading gyro. Having dual vacuum pumps means that if one pump fails, the other can usually provide enough suction to keep those critical instruments operating normally.
So you don't lose your primary attitude reference if one pump quits.
Exactly. This redundancy in both ignition and vacuum systems is a real cornerstone of the 172S's reputation for reliability and safety.
Okay, powerful and reliable engine with built-in backups. How do we actually control this thing once it's running? What are the pilot's main interfaces for the engine?
Engine power is primarily managed using 2 main controls right there in the cockpit, usually on the center pedestal or lower panel. First, you have the throttle. It's typically a black knob or lever.
Full forward for power, right?
Right. Pushed fully forward, the throttle is open for maximum power. Pulled fully aft, it's closed for idle power. There's also usually a small, round friction lock nut right at its base.
What's with that for?
You tighten that just enough so the throttle stays where you put it without you having to hold constant pressure. It prevents vibration from causing the throttle to creep back, a real wrist saver on longer flights.
Makes sense. And the other control?
The other main control is the mixture control. It's always a red knob, usually right next to the throttle. When it's pushed full forward, the mixture is set to full rich, meaning the engine is getting the maximum amount of fuel relative to air.
And pulled back?
Pulled fully aft, it's in the idle cutoff position. This completely cuts off the fuel flow to the engine, which is how you shut the engine down cleanly.
Okay. And you adjust it in between?
Absolutely. That red knob often has a little lock button on the end. If you press that button, you can make large, rapid adjustments, like pulling it quickly to idle cutoff. Or you can just rotate the knob clockwise or counterclockwise for small, very precise changes to the fuel-air mixture.
Why make those small changes?
That fine control over the mixture is absolutely vital. As you climb, the air gets thinner, less dense. To keep the fuel-air ratio correct for efficient combustion, you need to lean the mixture, reduce the amount of fuel going in.
Leaning.
Exactly. Proper leaning is crucial for efficient engine operation at different altitudes and power settings. It saves fuel, prevents spark plug fouling, and helps the engine run smoother and cooler. Learning to lean correctly using instruments like the EGT gauge is a key skill every pilot needs to master.
Got it. Throttle for power, mixture for fuel-air ratio. Okay, beyond the core engine itself, what are the essential support systems that keep it running smoothly and reliably day in, day out? Thinking about oil, air intake, exhaust, cooling.
You're thinking like a pilot already. Spot on. Several critical systems work together. Let's start with the engine lubrication system. We mentioned it's a wet sump type.
Oil in the pan at the bottom.
Right. The total system capacity is 9 U.S. quarts. That includes 8 quarts in the sump itself and about 1 quart in the oil filter. Now, your POH is very clear on operating limits. You must not operate with less than 5 quarts.
Minimum. That's scored.
Minimum 5. And 8 quarts are recommended for extended flights to ensure adequate supply and cooling. The POH also gives specific guidance on the types of oil to use different grades and viscosities depending on the outside air temperature.
So you use different oil in summer versus winter?
Potentially, yes, based on the temperature ranges. The key takeaway for a new pilot is always use the correct oil grade and viscosity for the current conditions, especially during the first 50 hours of a new or overhauled engine, where a specific straight mineral oil is typically required for proper break-in before switching to the more common ashless dispersant oil.
Break-in oil, okay.
And, of course, regular oil quantity checks during pre-flight are absolutely non-negotiable. You visually check that dipstick every time.
Okay, lubrication covered. What about ignition and starting?
The ignition and starter system is next. We already hit the dual magnetos, 2 independent systems, 2 spark plugs per cylinder. That redundancy is key.
Right.
The ignition switch itself is a rotary switch. It typically has positions for O off, R for right magneto only, L left magneto only, both, which is your normal operating position, using both magnetos for complete combustion and safety, and then a spring-loaded start position.
So we check L and R during the run-up, but fly on both.
Exactly. That both position ensures peak performance and provides that safety backup.
Okay. How does the engine get its air?
That's the air induction system. Ram air, just the air being forced in by the plane's forward movement, enters through an intake opening on the lower front part of the engine cowling. It then passes through an air filter to clean out dust, bugs, debris.
Standard air filter. Is there a backup?
Yes, and this is a critical safety feature. Inside the air box, right after the filter, there's a spring-loaded alternate air door. If your main air filter ever gets completely blocked, maybe by ice or a bird strike or just extreme dust.
Engine could suffocate.
Exactly. But the engine suction itself will automatically pull open this alternate air door. It then draws air directly from inside the engine cowl area. It's unfiltered air, mind you.
So not ideal.
Not ideal, but much better than no air. The trade-off is you'll get an approximate 10% power loss at full throttle when that alternate air door opens because the air isn't being rammed in as efficiently. But it ensures the engine keeps running, which is the priority.
Good backup to have. What about getting rid of the exhaust?
The exhaust system is pretty straightforward. Exhaust gas from each cylinder goes through riser assemblies into a muffler, similar to a car's, and then out through a tailpipe. But here's a cool connection. Built around the muffler are shrouds, sort of like metal jackets.
Shrouds. What for?
These form heating chambers. Outside air is ducted into these shrouds, gets heated up by the hot exhaust muffler, and then that hot air is piped into the cabin to provide cabin heat.
So our cabin heat comes directly from the exhaust system.
Indirectly, yes. The heat source is the exhaust. It's a simple, effective, and basically free heating system.
Right.
But it also means that checking the exhaust system for any leaks during pre-flight is extra important. Not just for engine health, but to prevent dangerous carbon monoxide gas from potentially leaking into that cabin heat air.
Very important check. Okay, how does the engine stay cool? It's air-cooled, right?
Correct. The cooling system relies entirely on airflow. Ram air enters through those two main intake openings in the front of the engine cowling. Inside, there's a system of carefully designed metal plates called baffling. Yeah, this baffling directs the airflow tightly around the cylinders and other hot engine components to maximize heat dissipation. The heated air then exits out the bottom rear edge of the cowling. The design is efficient enough that the 172S doesn't need manually adjustable cowl flaps like some other aircraft, but it means the condition of that baffling is critical. Any leaks or damage can significantly reduce cooling effectiveness.
Good to check during pre-flight then. Lastly, the propeller.
Finally, the propeller. On the 172, it's typically a fixed-pitch, two-bladed metal propeller around 76 inches in diameter. Fixed pitch is the key term here.
Meaning the angle of the blades doesn't change.
Exactly. The angle of attack of the propeller blades is constant. This design simplifies operation and reduces cost and maintenance compared to a constant-speed propeller where the pilot can adjust the blade angle.
What is the downside?
The downside is a performance trade-off. A fixed-pitch prop is optimized for a specific phase of flight, usually cruise. It won't be optimally efficient during takeoff and climb or at very high speeds compared to a constant speed prop that can adjust its bite. Understanding this helps you appreciate why certain climb or cruise speeds are recommended in the POH. They represent the best compromise for that fixed-pitch design.
Got it. Simple, reliable, but with inherent performance characteristics. Okay, let's shift gears. Fuel. Fuel is life in the air, right?
Absolutely.
Managing it properly is probably one of the most critical skills for any pilot, especially new ones. Let's dive deep into how the 172S manages its fuel capacity, distribution, monitoring. This seems like an area where mistakes can have serious consequences.
You're absolutely right. Fuel management or mismanagement is unfortunately a recurring theme in incident reports. So let's break it down carefully. First up, capacity. The total fuel capacity in a standard 172S is 56.0 U.S. gallons.
Okay, 56 total. How is it split?
It's split evenly between two wing tanks, so 28.0 gallons per tank. However, and this is a critical detail often missed or misunderstood by new pilots, only 53.0 U.S. gallons are usable.
53 usable, so 26.5 gallons per tank are usable.
Exactly. That means there are 3 gallons, 1.5 per tank, of unusable fuel. This is fuel that cannot be reliably fed to the engine in flight due to the tank design, the location of the fuel pickups, or maybe certain flight attitudes.
So you can't count on that last 3 gallons.
Never. Ever. You always plan your flight based on the usable fuel quantity, 53 gallons max in this case. Don't ever assume you can somehow access those last few gallons. That's your absolute emergency reserve, and you shouldn't plan to use it.
Crystal clear. Usable fuel only for planning. How does the fuel get from the tanks to the engine?
Okay, fuel distribution. Fuel flows by gravity from the 2 wing tanks down to a fuel selector valve. This valve is usually located on the floor at the base of the center pedestal between the front seats.
And it has different positions?
Yes. Typically, it has positions for both, left tank only or right tank only. Now, here's another crucial operating limitation stated clearly in the POH. You must take off and land with the fuel selector valve in the both position.
Must be on both for takeoff and landing. Why?
It's a safety measure. It ensures the engine is drawing fuel from both tanks simultaneously. This mitigates the risk of the engine quitting during a critical phase of flight, like takeoff or landing, because you accidentally had the selector on a single tank that might have run dry unexpectedly, or maybe has water contamination the other tank doesn't.
Makes sense. Use both when it matters most. How do we know how much fuel we have?
Fuel indicating is handled by 2 float-type fuel quantity transmitters, one inside each wing tank. These floats basically bob up and down with the fuel level.
Like the float in the toilet tank.
Pretty much the same principle, yeah. These transmitters send electrical signals to the fuel quantity indicator gauges on the instrument panel, usually 2 separate needles or 1 gauge with L&R indicators.
Okay. And when the gauge reads empty?
When a gauge shows empty, typically indicated by a red line and maybe a 0 or an E. Remember what we said about unusable fuel? That empty reading actually means there's still approximately 1.5 gallons of unusable fuel remaining in that tank.
So E doesn't mean completely empty.
Correct. Also very important, because these are float-type gauges, they are most accurate in level, unaccelerated flight. They can give misleading readings during slips, skids, steep turns, or even on sloped ramps.
So don't rely solely on the gauges.
Never rely solely on the gauges. Always, always visually check your fuel quantity with your own eyes using a dipstick or by looking in the tanks before flight. And in flight, use time and fuel burn calculations or a fuel totalizer if equipped to cross-check your fuel status. The gauges are just one piece of the puzzle.
Good advice. What about warning systems if the fuel gets really low? Does the plane yell at you?
It does, thankfully. There's a sophisticated low fuel warning system. If the fuel in either tank drops below approximately 5 gallons and stays there for more than about 60 seconds, an amber low fuel message will start flashing on the annunciator panel up top.
Flashing first.
Yeah, it flashes for about 10 seconds to really grab your attention. Then it goes to a steady amber light. Depending on which tank is low, you'll see messages like, ooh, low fuel, left tank low fuel R, right tank low. Or if both are low, L low fuel R.
Clear indication. That's good.
It's not just a gentle reminder. It's a clear caution message telling you to land soon. And the system is smart, too.
How so?
If one of the fuel transmitters itself fails, the system is designed to prevent giving you a false high rating, which could be disastrous. Instead, if a transmitter fails, its corresponding fuel level needle on the gauge will drop below the E mark, often pointing to an off-air position, and the relevant amber annunciator, L low fuel or low fuel R, will illuminate.
So a failure looks like an empty tank plus a warning light.
Exactly. It alerts you to a sensor problem rather than giving you a dangerously misleading reading suggesting you have more fuel than you actually do.
Clever. I heard some later 172S models have a fuel return system. What's that about?
That's right. Starting with serial number 172S9491, they added a fuel return system. This system basically sends a small amount of metered fuel from the engine's fuel air control unit back to the fuel reservoir tank.
Why do that?
Its main purpose is to help promote smoother engine operation, especially in very hot weather conditions. By circulating the fuel, it helps lower the temperature of the fuel reaching the engine inlet and minimizes the formation of fuel vapor in the line's something called vapor lock, which can interrupt fuel flow.
So an improvement for hot weather reliability.
Essentially, yes. A subtle but important upgrade for certain operating conditions. Now, the POH also spells out some critical fuel limitations that every pilot absolutely must know and respect.
Like what? Give us the highlights.
Okay, for example, if you're flying on one tank and it runs dry, you have a maximum slip or skid duration of only 30 seconds, any longer, and you risk unporting the fuel pickup in the other tank due to the sustained side slip angle.
Wow, only 30 seconds.
Yeah. Also, operation on either the left or right tank is limited to level flight only. No climbs or descents if you're not on both.
Level flight only on single tank. Got it.
And if you have 14 tang of fuel or less in a tank, prolonged, uncoordinated flight like sloppy turns with the ball out of center is prohibited when operating on that tank. Again, it's all about preventing fuel starvation by uncovering the fuel pickup port.
Makes sense. Keep the fuel over the pickup.
Exactly. And finally, approved fuel grades are 100 LL, the blue stuff, and 100 grade, the older green stuff, less common now. Using a lower grade like automotive gasoline is absolutely forbidden and can destroy the engine.
Stick to the approved aviation fuel. Okay, I can't stress enough how important those limitations are. And before every single flight, you're always down there with a sampler cup, right? Draining fuel.
Absolutely non-negotiable. This is a cornerstone of your pre-flight inspection. The 172S fuel system is equipped with multiple fuel drain valves. You need to know where they all are.
Where are they, typically?
There are sump drains under each wing tank, usually at the lowest point. There's a drain for the fuel reservoir sump, often near the firewall. There's a drain associated with the fuel selector valve itself. And there's a drain at the main fuel strainer, also usually near the firewall.
So quite a few places to check.
Yes, and you check them all, every time. Before each flight, and especially after each refueling, you're looking primarily for water, which is heavier than fuel and will sink to the bottom, appearing as clear bubbles or a distinct layer, and also for sediment or other contaminants.
Enough you find water.
If you find any water or contamination, you don't just drain a little and go. You must take further samples, maybe gently rock the wings to dislodge any trapped water, and keep draining until you get consecutive samples of pure, clean fuel from all drain points. Ignoring this step is just asking for engine failure. It's that serious.
Drain until clean. Got it. What about additives? Does the POH mention anything like fuel anti-icing?
It does, yes. The POH discusses fuel additives. Specifically, it mentions that isopropyl alcohol, or DiGME, diethylene glycol monomethyl ether, can be added to the fuel to prevent fuel icing, which can happen if water suspended in the fuel freezes and blocks lines or filters.
So helpful in cold weather.
Potentially, yes. But the POH outlines very precise mixing ratios, typically around 1% for alcohol or 0.10% to 0.15% for DiGME. It also warns that exceeding these ratios can actually be detrimental to fuel system components.
So precision is key. Don't just dump some in.
Absolutely not. The takeaway is that anti-icing additives are available and can be important, but they must be used exactly according to the approved procedures and concentrations, like following a recipe carefully. The manual even notes that water can leach out the additive during prolonged storage, so you might need to check the concentration. It just shows how even seemingly small things require precision and understanding.
Wow. Fuel system deep dive complete. Okay, let's switch to electrons. So much of what we do in a modern cockpit relies on electricity radios, GPS, lights, even the flaps we talked about. How is the 172S wired up? What are the main parts of its electrical system?
Right, the electrical system is pretty central. The airplane operates on a 28-volt direct current DC electrical system. Think of it like a car system, but running at a higher voltage, 28 volts nominal, compared to a car's 12 volts.
Okay, 28 volts DC. Where does the power come from?
Two main sources. The primary source when the engine is running is a belt-driven 60-amp alternator, that's your generator, constantly producing power. The second source is a 24-volt battery, which acts as a storage device, provides power for starting the engine, and serves as a backup if the alternator fails.
Where's the battery usually located?
It's typically mounted on the left forward side of the firewall inside the engine compartment. Now, how the power gets distributed is important. Power is supplied through a split primary bus bar. You can think of a bus bar as a central distribution point, like a power strip. Having it split means there are essentially two main electrical pathways.
For redundancy.
Partly, yes. And connecting these two primary buses is something called the essential bus. This special bus ensures that critical items always have power available from either side. Things like the master switch circuit itself, the annunciator panel lights, your warnings, and some interior lighting run off this essential bus.
So the absolute must-haves stay powered.
Exactly. Each primary bus also connects via a single avionics master switch to an avionics bus bar. These avionics buses power your radios, GPS, transponder, all the sensitive electronic navigation and communication gear.
Okay, so we have primary buses, an essential bus for critical stuff, and avionics buses for the radios. Let's talk switches. The big red master switch everyone learns. First, it has two sides, right? BAT and ALT.
Correct. The master switch is actually two switches combined. The side labeled BAT, battery, connects the battery to the primary buses, essentially turning the airplane's main electrical system on.
Okay, B turns the power on. What about ALT?
The ALT, alternator side, connects the alternator's output to the electrical system. So with both sides on, which is the normal state in flight, the alternator is powering all the sisters and recharging the battery.
What happens if you turn just the ALT side off?
Crucially, if you turn the ALT side off while leaving the BAT side on, the entire electrical load of the aircraft is placed directly onto the battery. The alternator is disconnected.
So the battery starts draining.
Immediately. This highlights why managing your electrical load is so important if the alternator fails. You need to shed non-essential loads quickly to conserve battery power. The POH warns that continued operation with the alternator off can deplete the battery to the point where the battery contactor opens, and you might not be able to restart the alternator even if you fix the issue.
Good to know. And the separate avionics master switch? Why have that?
The avionics master switch specifically controls power just to those avionics bus bars. Its main purpose is to protect your sensitive and expensive radios, GPS units, etc. during engine start.
Protect them from what?
From voltage spikes. The engine starting process, especially the starter motor engaging and disengaging, can create significant electrical surges or transients on the electrical system. These spikes can easily damage delicate avionics.
So that's why the checklist always says avionics master off before starting the engine.
Exactly. The POH explicitly warns, do not crank or start the engine with the avionics master switch in the on-end position. Always wait until the engine is running smoothly before turning the avionics master on.
Got it. How do we monitor the health of the electrical system?
You have an ammeter, usually located on the lower left side of the instrument panel. This gauge shows the flow of current.
What does it tell us specifically?
If the needle shows a positive reading, charging, it indicates the rate at which the alternator is charging the battery. If it shows a negative reading, discharging, it means the battery is supplying current to the system because the alternator isn't keeping up with the load or has failed.
Okay, positive charge, negative discharge.
Right. You also have a low voltage annunciator light. This amber light will illuminate if the system voltage drops below a certain threshold, typically around 24.5 volts.
When might that happen?
It often flickers on during taxi at low RPMs, especially if you have a lot of electrical equipment turned on, like landing lights or pitot heat. At low engine speed, the alternator might not be spinning fast enough to meet the full demand.
So not necessarily a failure?
Not necessarily. It usually goes out as soon as you increase RPMs for takeoff. But if it stays on or comes on in flight at normal cruise RPM, that indicates a potential problem with the alternator or charging system that you need to address using the checklist.
Okay. What about protection? Fuses? Breakers?
Both. Most of the internal circuits are protected by circuit breakers. These are typically push-to-reset types, or sometimes rocker switches that double as breakers. Think of them as reusable fuses.
Right, you can reset them once.
Exactly. The procedure is usually to wait a moment for it to cool, then push it back in once. If it pops out again immediately, you don't keep pushing it. That indicates a persistent fault. Additionally, the main power distribution module, often behind the panel, uses some automotive-style spade fuses and maybe a glass fuse for things like the clock. Your POH might even show where spare fuses are located, often right inside that module, a nice touch.
Good to know spares might be on board. What about external power for starting?
The POH mentions that a circuit exists to allow the battery contactor to close when external power from a ground power unit is applied. This can help with starting if the aircraft battery is low.
So a jump start, basically.
Essentially, yes, but the manual emphasizes this is a servicing aid and not a substitute for proper battery maintenance. Don't rely on ground power just because you haven't taken care of your battery.
Good point. Maintain your systems. Okay, that covers the juice. Let's look at the instrument panel, our window into the aircraft health, and our connection to the outside world. What are the key indicators and alerts we need to know? How's it all laid out?
Right. The instrument panel in the 172S is typically an all-metal panel, and it's often designed in segments. This is actually a neat feature for maintenance, as related instrument groups can be removed without taking the whole panel apart.
Practical. How's the layout for the pilot?
On the pilot side, usually the left seat, the primary flight instruments are arranged in the standard basic T configuration. This is really important for your instrument scan.
The T. Remind us what that is.
The gyroscopic instruments, your attitude indicator, artificial horizon, and your directional indicator, heading gyro, are stacked vertically right in front of you over the control column. To the immediate left of the attitude indicator is the airspeed indicator, and to the immediate right is the altimeter. That forms the T.
Airspeed, attitude, altimeter across the top, heading indicator below attitude. Got it.
Exactly. This layout is standard across most aircraft and makes for a very quick, intuitive scan between your most critical flight instruments. Now, around this basic T, you'll find other instruments.
What else is typically there?
To the left of the main flight instruments, often in a sub-panel, you'll find gauges like fuel quantity, oil temperature, and pressure. The vacuum system gauge combined with the ammeter, maybe an EGT fuel flow indicator, the digital clock OAT indicator, and down below that, the avionics circuit breaker panel.
Okay, engine and system instruments to the left. What's to the right?
To the right of the T, you'll usually find the tachometer, engine RPM, and various navigation instruments like VOR or GPS indicators, depending on the avionics installed. The whole layout is designed for efficient pilot scanning, minimizing eye movement between related instruments.
Makes sense. What about warning lights? How does the plane get our attention?
That's the job of the annunciator panel. It's usually a rectangular panel located prominently, often right above the altimeter or attitude indicator. This panel is your aircraft's direct communication system for warnings and cautions.
Red and amber lights.
Exactly. It provides crucial caution messages, usually amber, and warning messages, always red. Things like low fuel, low oil pressure, low volts, vacuum failure. And here's a neat feature. When a new message illuminates, it typically flashes for about 10 seconds before becoming steady.
Why the flashing?
It's specifically designed to grab your attention immediately, even if you're focused elsewhere. It's hard to miss a flashing light right in your line of sight. After 10 seconds, it goes steady so it's less distracting, but still clearly visible.
Smart. Where do the signals for these lights come from?
Inputs come from critical sensors all over the aircraft. The fuel quantity transmitters, the low oil pressure switch, vacuum system pressure transducers, the alternator control unit. There's usually also a dimmer control or a day-night switch linked to this panel to adjust the brightness. This panel is truly your aircraft yelling at you when something needs urgent attention. Understanding every light on it is paramount.
Absolutely. What other key engine instruments are there besides the annunciators?
Beyond the warning lights, you have dedicated gauges. There's the combined oil pressure and oil temperature indicator. There's the engine-driven mechanical tachometer, which shows engine RPM, and also includes an hour meter, often called a Hobbs meter, to record engine operating time.
Right, the Hobbs meter for logging flight time.
Well, sort of. Interestingly, the low oil pressure switch, the one that triggers the red oil press annunciator if pressure drops below about 20 psi, is often also wired to the Hobbs meter.
What does that mean?
It means the Hobbs meter only records time when there is sufficient engine oil pressure. So it's really measuring engine running time, not just time the master switch is on. A subtle but important detail for accurate logbook entries and understanding maintenance intervals based on actual engine operation.
Huh. Good to know. What else for the engine?
You'll also have an exhaust gas temperature, EGT, indicator, which is crucial for leaning the mixture properly, as we discussed. Sometimes this is combined with a fuel flow indicator.
Okay. Now, what about the instruments that rely on air pressure, airspeed, altitude, vertical speed?
Right. That's the pitot-static system and its instruments. These are fundamental to flight. The system uses pressure sensors connected to the pitot tube and static ports.
Pitot tube measures ram air pressure for airspeed. Static ports measure ambient air pressure for altitude and vertical speed, right?
Exactly. A key component here, especially for flying in potentially icy conditions, is the heated pitot system. There's an electrical heating element inside the pitot tube to prevent ice from blocking the opening.
Because if the pitot tube ices over,
your airspeed indicator becomes unreliable or completely useless. Very dangerous. This system is controlled by a switch breaker, usually labeled pitot heat, on the lower left panel. Using it proactively in visible moisture near freezing temperatures is critical.
Okay. What if the static ports get blocked? By ice or maybe a bug?
Good question. That would cause errors in your altimeter, vertical speed indicator, and even the airspeed indicator. To counter this, the 172S has a static pressure alternate source valve.
An alternate source? Where does it get the pressure from?
It's usually located below the throttle or somewhere accessible on the lower panel. When you activate this valve, it allows the static system to draw pressure from inside the cabin instead of the external ports.
So it's a backup. Does it read accurately?
It provides a usable static source, ensuring you retain critical airspeed, altitude, and VSI information. However, cabin pressure is usually slightly lower than outside static pressure, so the readings might have some error. Section 5 of your POH usually has a calibration table showing the expected difference when using the alternate source. Knowing this backup exists and how to use it can be a lifesaver, especially in IFR conditions.
Definitely good to know that's there. Okay, what about the vacuum system instruments? The gyros.
Right, the vacuum system and instruments. As we mentioned, this system typically powers your attitude indicator, artificial horizon, and directional indicator, heading gyro.
And it has dual pumps for redundancy.
Correct. The system usually consists of 2 engine-driven vacuum pumps, pressure switches to monitor their output, a vacuum relief valve to regulate the suction, an air filter, and a manifold with check valves. These check valves ensure that if one pump fails, the other can take over without suction being lost back through the failed pump.
How do we know if there's a problem?
Besides the main vacuum gauge, the annunciator panel provides early warning. Amber messages like LVAC, left pump low, VAC, right pump low, or LVACR, both low, will flash if the suction from a pump drops below a certain threshold, typically around 3.0 inches of mercury.
So you get a heads up before the instruments fail completely.
Ideally, yes. This alerts you immediately to a partial or complete vacuum system failure, meaning your gyroscopic instruments are becoming unreliable or will soon fail. Now, the directional indicator, or DI, is a vacuum-driven gyro that shows your heading, but it's important to remember how it works.
It's not a magnetic compass, right? It drifts.
Exactly. It's a gyro, and gyros suffer from something called precession. Precession is just a natural tendency for the gyro to drift slightly over time due to friction and the Earth's rotation.
So it doesn't stay perfectly aligned with north?
No, that's why you need to periodically check it against your magnetic compass, which always points to magnetic north, though it can be bouncy in turbulence, and manually reset the DI using the adjustment knob. Your POH reminds you to set it with the magnetic compass just prior to takeoff and periodically in flight. It's a key part of your instrument scan to ensure your primary heading reference remains accurate.
Got it. Reset the DI regularly. What about stall warnings?
A crucial safety feature, the stall warning system. In the 172S, it's typically a pneumatic-type system. There's a small inlet on the leading edge of the left wing.
What does it do?
As the wing approaches its critical angle of attack, just before it stalls, the airflow changes over that inlet, creating a pressure differential. This differential pressure activates an air-operated horn, literally a reed horn located near the upper left corner of the windshield inside the cabin.
So you get an audible warning.
Yes, a distinct buzzing or horn sound. It's designed to activate typically 5 to 10 knots above the actual stall speed, giving you an early warning in all flap configurations. This audible cue is an essential alert that you're approaching a stall and need to take immediate corrective action like lowering the nose.
Good, loud warning. Any other standard instruments?
Most 172S panels also include an integrated digital clock OAT indicator, outside air temperature voltmeter, as a standard feature. Very handy for time, temperature checks, and keeping an eye on system voltage all in one place.
Okay, comprehensive panel. Now, don't forget, we need to see and be seen, especially flying at night or in reduced visibility. How are the lighting systems handled in the 172S?
Good point. Proper lighting is essential. The 172S has both interior and exterior lighting systems, although the base POH often focuses more on the interior details.
Let's start inside. How do we light up the panel?
For interior lighting, the instrument panel itself typically uses individual post lights or lights mounted directly within the instruments and gauges. The brightness of all these is usually controlled by a single dimmer knob labeled Panel LT or similar. Rotate it clockwise, things get brighter.
Okay. Any other interior lights?
Yes, the pilot's control wheel often has its own dedicated light, sometimes called a map light or yoke light. It's usually controlled by a separate rheostat knob right on the yoke itself. This provides downward illumination onto the pilot's lap area, really handy for checking charts, approach plates, or making notes without ruining your night vision or creating glare on the windshield. You usually need to have the navigation lights turned on for this one to work, though.
Ah, good tip. What about the avionics displays?
The brightness of the avionics displays themselves and often the NAV indicator lights is usually linked to the annunciator panel test dimmer switch. There are typically BRT day and dim night settings that affect multiple displays simultaneously.
Got it. What if a light burns out or stops working? Troubleshooting.
Your POH usually states the obvious. The most probable cause of a single light failure is simply a burned out bulb. However, if a whole system of lights fails, you should first check the relevant circuit breaker.
Reset it.
The procedure is turn off the switch for the affected lights, reset the breaker once, then turn the switch back on. But here's the critical warning. If that breaker trips again immediately, do not reset it again.
Why not?
Because that indicates a persistent electrical fault, like a short circuit. Repeatedly resetting it could overheat the wiring and potentially cause a fire. It means the system needs maintenance attention, not just another reset.
Okay, sound advice. Let's transition inside the cabin itself, making sure we're comfortable and, more importantly, safe. What does the POH tell us about the cabin environment and occupant safety features?
Absolutely. Pilot and passenger comfort and safety are key design considerations. For heating, ventilating, and defrosting, warm cabin air, remember, heated by the exhaust shroud, and outside fresh air are supplied to the front cabin through outlets usually located near the pilot's and co-pilot's feet. You control the amount of heat and fresh air with push-pull knobs.
What are the back seats?
Rear cabin heat and air are typically ducted down each side of the cabin to outlets back there. Windshield defrost air also comes from this same system, ducted up to adjustable outlets along the base of the windshield, letting you direct airflow to keep it clear.
And fresh air vents.
Yes. In addition to the main heating ventilating system, there are usually separate adjustable fresh air ventilators, often overhead or on the side panels, providing additional airflow for all occupants. You can twist or position these to direct cool air where you want it.
Okay, staying comfortable. What about the seats themselves?
The 172S typically features 2 individually adjustable crew seats up front for the pilot and front passenger, and usually a single bench-style seat for rear passengers.
How adjustable are the front seats?
Pretty adjustable, which is important for reaching the controls properly. They usually slide fore and aft using a lever underneath. They often have height adjustment, sometimes using a large crank handle on the side. And the seat back angle can typically be adjusted using a release button or lever. The rear seat might have a simpler reclining back feature. Headrests are usually adjustable on all seats, too.
Why is proper seat adjustment so crucial?
It's not just about comfort. It's critical for safety and control. The pilot needs to be positioned to have full, unrestricted movement of the flight controls, especially the rudder pedals, full deflection, and the yoke, full travel, without stretching or being cramped. You need to be able to see clearly over the panel, too. Taking a moment to get the seat perfectly adjusted before flight is really important.
Good point. What about keeping occupants safe? Belts and harnesses.
Yes. For occupant safety, all seat positions in the 172S are equipped with integrated seatbelt and shoulder harness assemblies. These are usually a single buckle system connecting both lap and shoulder straps.
How do the shoulder harnesses work? Are they fixed?
No, they typically incorporate overhead inertia reels. These reels are mounted in the ceiling center line for the front seats, often outboard for the rear seats. The inertia reel allows the shoulder harness to move freely during normal movement, leaning forward, etc.
But they lock up in a crash.
Exactly. They lock automatically and instantly during any sudden deceleration, providing positive restraint in turbulence or, crucially, during an impact sequence. The POH strongly emphasizes verifying proper locking of the lap belt. It needs to be snug and low across the hips, with no more than 1 additional inch of belt able to be pulled out after buckling.
Snug lap belt is key.
Absolutely. And there's a critical safety note often included. If an occupant, like a small child, is too small for the restraint system to secure them properly, the aircraft should not be occupied by that person. Using unapproved child seats or booster seats is generally prohibited unless explicitly allowed by regulations or aircraft documentation. Safety first.
Very important consideration. Okay, what about getting in and out? Doors and windows.
Standard setup here. 2 main entrance doors, one on each side of the cabin. They usually have recessed exterior handles for aerodynamics, conventional interior handles, and typically a key lock on the pilot side, left door. Both front doors usually have openable windows as well, with latches.
Anything unusual about the doors?
Actually, yes, there's a great practical insight in the POH for new pilots regarding the doors. It notes that if a door accidentally pops open in flight, usually because it wasn't closed and latched properly before takeoff.
Which can be startling.
Very startling. But the POH explicitly states this does not constitute an emergency or necessarily require an immediate landing. The aircraft is designed to remain stable and controllable with a door open.
So don't panic. What's the procedure?
Don't panic. The recommended procedure is usually to slow the aircraft down a bit, maybe trim for around 75 knots indicated airspeed, then momentarily shove the door outward slightly into the slipstream. This helps equalize the pressure difference, and then pull it forcefully closed and ensure it's properly latched this time.
Shove it out first, then pull it in.
Counterintuitive, maybe, but it works. It's a great example of how knowing your aircraft's procedures straight from the POH can help you handle an unusual situation calmly and safely.
Definitely good to know that one. Okay, let's talk about when things go really wrong. Emergency systems and external safety features. These become paramount then.
Indeed. Knowing these systems well is critical for emergency preparedness. First up, the Emergency Locator Transmitter, or ELT.
The device that signals rescuers after a crash.
Exactly. In the 172S, it's often controlled by a remote switch and annunciator light located on the instrument panel, maybe on the co-pilot side. The annunciator light illuminates when the ELT is actively transmitting.
What frequencies does it use?
It transmits omnidirectional signals on the international distress frequencies, 121.5 megahertz, the civilian frequency, and sometimes also 406 megahertz, the satellite frequency on newer ELTs, and 243.0 millihertz, the military frequency.
How is it activated?
It's designed primarily to activate automatically. There's an internal G-switch, basically a sensor that detects sudden, strong deceleration forces, like those experienced during a crash impact. It can also be activated manually by the pilot using that remote switch on the panel.
Are there checks or maintenance required?
Oh yes, very strict requirements. The battery typically needs to be replaced based on a calendar date, often every 2 years, or after the ELT has accumulated 1 hour of total operational use. There are also specific operational tests required, usually done during inspections, and the POH outlines a strict procedure for brief pilot testing, often advising to do it only within the first 5 minutes after any hour to avoid interfering with satellite detection systems. It's a vital piece of safety gear that needs to be ready.
Okay, ELT covered. What about fire on board?
A cabin fire extinguisher is standard equipment. It's typically a portable unit filled with Halon 1211 or a similar approved agent. Its location is important, usually mounted on the floorboard near the pilot's feet or seat, making it immediately accessible in an emergency.
What checks are needed for the extinguisher?
Before every flight, you need to do 2 quick checks. First, check the pressure gauge. Make sure the needle is in the green arc, indicating it's properly charged, usually around 125 psi. Second, verify that the safety pin or operating lever lock pin is securely in place to prevent accidental discharge. It's a quick check, but essential. That extinguisher is your first line of defense against an in-flight cabin fire.
Check pressure, check pin. Got it. Anything else for external safety?
One other item often mentioned are static dischargers, sometimes called static wicks. These are small, pointed rods or braided wires usually attached to the trailing edges of the wings, elevator, and rudder.
What do they do?
Their purpose is to help dissipate static electricity that can build up on the airframe, especially when flying through precipitation, rain, snow, ice, or clouds. This buildup, called precipitation static or P-static, can cause significant interference and noise in your radio communications and navigation equipment.
So they make the radios clearer.
They help reduce the interference, yes. However, your manual will likely caution that even with static wicks, flying into severe precipitation can still cause radio signal loss or significant noise. They also lose effectiveness over time as they erode or get damaged, so they require periodic checks, usually during maintenance inspections. The best advice is still to avoid known areas of heavy precipitation whenever possible to maintain reliable communications.
Good advice. Okay, let's talk avionics. Modern cockpits, even in trainers like the 172S, are full of advanced electronics. What does the POH typically tell us about the standard and optional avionics packages? What are the crucial operational details for a new pilot to grasp?
Right, avionics can seem daunting at first. The base POH itself might only cover the very standard instruments, but it will always reference various supplements at the back of the manual for any installed optional equipment. These supplements are your go-to source for specific operating instructions for your aircraft's avionics fit.
So you need to check the supplements for your specific plane.
Absolutely. The POH might mention a standard avionics package or refer to common packages like NAVI, NAV2, maybe NAV2 with an HSI. While we can't detail every possible option here, it's vital to understand the types of systems you might encounter and their general functionality, focusing on how you interact with them as the pilot.
Okay. What are some key standard flight instruments we always expect to see?
From the basic equipment list, you'll always have your core flight instruments. The airspeed indicator, sensitive altimeter, magnetic compass, turn coordinator, and vertical speed indicator. Those are fundamental.
Right, the pitted static and basic gyro instruments. What about common communication and navigation systems mentioned in supplements?
Okay, looking at common supplements, you'll often find info on the NAV-TAMM radios. Systems like the Bendix King KX155A or KX165A are very common VHF and AV common units. They combine navigation, VORL, OTHI, and communication functions. A really valuable safety feature often included is a stuck microphone alert. If your microphone button accidentally gets stuck in the transmit position, the radio will automatically stop transmitting after about 30-35 seconds, and the frequency display might flash. This is incredibly important because a stuck mic can block all communications on that frequency for everyone in the area, including potentially blocking emergency calls. This feature prevents that.
Very useful safety feature. What about the transponder?
The transponder, maybe a Bendix King KT-76C or similar, is how your aircraft identifies itself to air traffic control radar. It replies to interrogations with a coded signal, your squawk code, and if it's a Mode C or Mode S transponder, it also reports your pressure altitude.
It shows altitude.
Yes, it often displays the altitude it's reporting, usually as FL for flight level, for example, FL065 for 6,500 feet. A neat safety check built in. If the transponder detects an invalid altitude code coming from the encoder, it will often display dashes instead of an altitude number.
Why is that good?
It prevents you from transmitting erroneous altitude information to ATC, which could lead to conflicts or misunderstandings. It tells you there's an issue with the altitude reporting system.
Smart. What about managing all the audio? Intercoms, Marker beacons.
That's the job of the audio selector panel, like a Bendix King KMA 26 or KMA 28. This unit acts as the central hub for all your audio. It's an amplifier, lets you select which radios you want to transmit on and listen to, controls the intercom system between occupants, and often includes the marker beacon receiver.
Marker beacons for instrument approaches.
Exactly. The audio panel will provide distinct flashing lights, usually blue for outer marker, amber for middle marker, white for inner marker, and corresponding audio tones. Low-pitch dashes, medium dot dashes, high-pitch dots, as you fly over the beacons on an ILS approach. Often there are sensitivity settings, high-low for the marker receiver too. It's key for situational awareness on approaches.
Okay, now GPS navigation systems. They're very common now.
Very common. Systems like the Bendix King KLN-89B or KLN-94 or Garmin equivalents use the Global Positioning Satellite Network for navigation. They are incredibly powerful tools, especially for instrument flight rules IFR operation.
What's critical to know about using them?
Several things. First, the database containing airports, waypoints, procedures, etc. must be current, especially for IFR flight and particularly for flying GPS approaches. Databases are typically updated every 28 days via subscription services like Jeppesen-Sanderson. Flying IFR with an expired database is generally prohibited or restricted.
Current database is key.
Absolutely. Second, the POH supplement will emphasize that GPS for IFR navigation requires careful waypoint verification and cross-checking with other navigation sources. Third, various GPS enunciators on the unit itself, like MSG for messages, WPT for waypoint alerts, ARM for approach arming, ACTV for active leg, APR for approach mode, provide critical status information that you must understand and monitor.
What about autopilot coupling?
Yes, some variants, the POH notes starting around serial number 172S9423, included automated roll steering capability when coupled with the KAP-140 autopilot. This means the autopilot can automatically sequence through waypoints in your GPS flight plan and make the turns for you, significantly reducing workload on cross-country flights.
Wow, an autopilot in a 172. That sounds advanced for a trainer.
Yeah.
What does the POH emphasize about its operation?
It is pretty advanced. If equipped, often with a Bendix King KAP-140 single or two-axis autopilot, it can be a great asset, but you need to understand it well. It has key modes like HG, follows the heading bug you set on the DG or HSI. NAV tracks a VOR or GPS course. APR tracks an ILS localizer or GPS approach course, sometimes with glide slope coupling. And REVBC for flying a back course approach.
Does it just fly the plane perfectly?
Not quite. It requires pilot management. For instance, the POH supplement will specify required airspeeds for certain operations, like maintaining maybe 90 knots indicated airspeed for autopilot-coupled approaches. You, the pilot, still need to set the course datum correctly using the heading bug or HSI course pointer. It often includes altitude hold, ALT, and sometimes vertical speed VS modes for climbs and descents. And enunciators like PCCH trim will alert you if the aircraft is out of trim and the autopilot is struggling to hold altitude.
So it assists, but doesn't replace the pilot.
Never replaces the pilot. You must always be monitoring it and ready to take over immediately.
Okay. What about older navigation systems like ADF? Are those still relevant?
You might still find an ADF, automatic direction finder, like a Bendix King KR87 installed. It navigates using ground-based non-directional beacons, NDBs. It usually includes a BFO, beat frequency oscillator mode.
BFO, what's that for?
Some NDBs transmit only a continuous carrier wave without an audible Morse code identifier. The BFO generates an internal tone that allows you to hear the Morse code identifier of these NDBs when you tune them in, so you can confirm you have the right station. The ADF also has ANT, antenna mode, for clearer audio reception, and ADF mode, where the needle points towards the station.
Are there quirks with ADF?
Oh, yes. The supplements often discuss operational considerations like night effect and mountain effect. Night effect happens because low-frequency radio waves from distant NDBs can bounce off the ionosphere at night, causing the ADF needle to swing erratically. Mountain effect is similar, where terrain reflects or blocks the signal. In these cases, the manual advises you to average the needle oscillations to get a general bearing. Rather than chasing a wildly swinging needle, it requires interpretation.
Good to know. What about an HSI? That combines heading and navigation, right?
Yeah. Exactly. If your 172S has an HSI, horizontal situation indicator, usually described in a supplement like Supplement 13, it's a fantastic instrument. It provides a combined pictorial presentation of your aircraft's heading, along with its deviation relative to a selected VOR or GPS course, or an ILS localizer beam. It often includes glide slope deviation indication as well.
So less scanning needed.
Much less scanning. It integrates heading and navigation information beautifully. It typically has a heading selector knob, the heading bug, a course selector knob to set your desired VOR GPS LOC course, and a course deviation bar, often called the D bar. A key thing to understand is that the sensitivity of that D bar changes depending on your navigation source.
How does it change?
For a VOR signal, full-scale deflection might represent 10 degrees off course. But for an ILS localizer, it becomes much more sensitive, maybe 2.5 degrees for full scale. And for GPS, it might be 5 nautical miles en route, narrowing down to only 0.3 nautical miles in approach mode. Understanding these scale changes is absolutely vital for flying accurately, especially on approaches.
Huge difference in sensitivity. Okay, multifunction displays, MFDs, moving maps.
Yes, you might find an MFD like a Bendix King KMD 550 or a Garmin unit. These use a joystick or knobs and function keys to display a moving map with your position, flight plan routes surrounding airports, navades, terrain, maybe even weather data overlaid. It connects to the GPS for position and flight plan information.
Is it a replacement for paper charts?
Absolutely not. The POH supplement will strongly emphasize that the MFD is a navigation aid for enhancing situational awareness, but it is not approved as a primary navigation source or a replacement for current approved paper charts or electronic flight bag data. It's a great tool, but it's supplemental.
Situational awareness tool, not primary navigation. Got it. Any other supplemental systems we should touch on?
One more that sometimes appears is a 12-volt cabin power system, basically a cigarette lighter-style power outlet.
For charging phone?
Possibly, but with major restrictions. The supplement will state it's not certified for powering flight-critical devices. Its use is often prohibited during takeoff, landing, and any IFR flight, unless specific radio interference checks have been done and documented. It's usually limited to maybe 10 amps maximum. And crucially, there's often a prohibition against using it to charge lithium batteries due to the potential risk of fire or explosion associated with charging those batteries in an aircraft environment.
Wow, even a power outlet has strict rules.
It highlights how even simple conveniences in an aircraft have safety implications and strict limitations that pilots must be aware of and adhere to. Always check the supplement.
Absolutely. Check the POH and its supplements for your specific aircraft configuration. Okay, understanding all these systems in isolation is one thing, but the real payoff comes when we connect this knowledge to our day-to-day flying, right? How does knowing the details of the fuel system or the electrical system directly impact normal operations?
This is exactly where the knowledge becomes practical skill. Every single system we've discussed feeds directly into your normal operating procedures, making that POH your essential guide, not just something you read once for the check ride. Let's walk through a typical flight.
Okay, start with pre-flight.
Pre-flight inspection. Your systems knowledge is everything here. Knowing the location of all those fuel system drain points, wing tanks, reservoir, selector, strainer is fundamental for that critical check for water and sediment. You visually check fuel levels against what the gauges say. You ensure the alternate air intake isn't obstructed. You test the pitot heat, feel for warmth carefully. You perform the annunciator panel test to make sure all warning lights work. You physically remove the control lock because you know what happens if you forget.
Right.
You check tire inflation, look for obstructions around flight controls, check oil level. Without knowing where to look and why you're looking, your pre-flight is just a walk-around, not an inspection.
Okay, pre-flight done. Engine start and taxi.
Engine start and taxi. Your systems knowledge guides you here too. After start, you're specifically looking for oil pressure indication within a certain time frame, maybe 30 seconds in summer, maybe up to a minute in very cold weather. If you don't see it, you know to shut down immediately because the lubrication system isn't working.
Makes sense.
You use specific throttle and mixture settings based on the POH procedures if the engine is flooded. You're acutely aware of the danger zone around the propeller arc if anyone is nearby, treating it as if the ignition is always live. And when taxiing, especially over loose gravel or rough surfaces, you use slow engine RPM specifically to protect those propeller tips from nicks and damage because you understand how critical propeller condition is.
Good habits based on system knowledge. What about takeoff and climb?
Takeoff and climb. Again, systems knowledge dictates procedure. You might lean the mixture slightly even for takeoff if you're at a high elevation airport, following POH guidance to get maximum rated power from your fuel-injected engine. You use specific flak settings, like 10 degrees for short field, maybe 0 for normal, based on performance needs. You know and use the correct rotation and climb speeds best rate, V, like 74 kS, and best angle, VX, like 62 kS at sea level.
Right.
You monitor engine temperatures during the climb, understanding that proper cooling relies on airflow and that baffling system.
Okay, how about cruise flight?
In cruise, your manual might recommend cruising at a slightly higher power setting, maybe 75% for the first 50 hours of a new or overhauled engine. Why? To ensure proper seating of the piston rings for long-term engine health. That's direct system knowledge influencing operation.
Right, engine break-in.
And, of course, leaning the mixture properly in cruise is critical. You use the EGT gauge or fuel flow indicator, following POH procedures to lean for best economy or best power, saving fuel and keeping the engine happy. The POH also often includes specific procedures for managing potential fuel vapor issues in hot weather, emphasizing how to adjust mixture, fuel pump usage, if applicable, and engine speed based on your understanding of how heat affects the fuel system.
Okay, bringing it in for landing.
Landing. Systems knowledge dictates your configuration and speeds. Approach speeds vary with flap settings, typically 65-75 kS with flaps up, but slowing to 60-70 kS with full flaps, 30 degrees. For a normal landing, you aim to touch down on the main wheels first, gently lowering the nose wheel because you know the nose gear isn't designed for the primary impact. You use minimum braking necessary.
What about short or crosswind landings?
For a short field landing, you'd use full flaps, 30 degrees, and maintain a precise approach speed, like 61 kS, then apply heavy braking immediately after touchdown. For crosswind landings, you typically use minimum necessary flaps and apply specific control inputs like the wing-low method, using your understanding of how ailerons and rudder work together to maintain control despite the wind. Each procedure directly leverages your knowledge of the aircraft's systems and aerodynamics.
It all connects. What about after shutting down?
Post-flight and maintenance awareness is important too. Your manual stresses the importance of regular inspections, like the annual and 100-hour inspections. It details proper ground handling, tie-down procedures, and, crucially, emphasizes checking that fuel filler caps are secure and vents are clear to prevent fuel contamination or loss, and to allow for expansion contraction. Even details about propeller care, like how to address small nicks and why you should never use harsh alkaline cleaners on it, are rooted in maintaining system integrity.
That really paints a clear picture of how system knowledge is woven into every phase of flight. Now, let's talk emergencies. When a system fails, that knowledge truly becomes your most powerful tool, right? What emergencies listed in the POH really highlight the importance of this deep system understanding?
Absolutely. Emergency procedures are almost entirely based on understanding system behavior and knowing exactly how to manipulate the controls to mitigate the failure. Take the big one. Engine failure.
Okay.
The checklist procedure, like for an emergency landing without engine power, involves immediate specific actions. Establish best glide speed, maybe 70 kS flaps UP, 65 kS flaps down. Move the mixed control to idle cutoff. Pull the fuel shut-off valve to ROF. Turn the ignition switch off F. Maybe turn the master switch off just before touchdown.
Why those specific actions?
Each action directly manipulates a critical system based on understanding the failure. Cutting fuel and ignition prevents reignition or fire. Setting best glide speed maximizes your time aloft. Turning off the master reduces fire risk on impact. It's all about controlling the systems you still can control.
Makes sense. What about fires?
Fires are another prime example where system isolation is key. For an engine fire in flight, the immediate actions are usually mixture to idle cutoff, fuel shutoff valve, OBF, auxiliary fuel pump, OFF, if applicable, master switch, OFF. You're immediately cutting off the fuel supply and electrical power to the engine compartment to starve the fire.
And an electrical fire.
For an electrical fire in flight, the focus shifts, usually. Master switch OFF immediately to kill power to almost everything. Then close all cabin vents to cut off oxygen flow. After that, the checklist might guide you through trying to isolate the faulty circuit by turning off individual breakers or switches, then carefully restoring power only to essential items if possible, being careful not to reset a breaker that keeps tripping because you know that indicates the source of the fire.
Understanding the electrical system layout is crucial there.
Absolutely. Electrical malfunctions in general require system knowledge. If your ammeter shows an excessive charge rate, or zero charge, or if the low voltage light comes on and stays on, specific checklists guide you through troubleshooting the alternator and battery system, managing electrical load, and making a decision to terminate the flight safely. Again, the POH warns against repeatedly resetting a tripped breaker.
Okay. What about icing?
Icing encounters demand immediate use of relevant systems. If you inadvertently fly into icing conditions, the checklist will say, pitot heat on N, because you know your airspeed indicator is critical.
Mhm.
Maybe turn up cabin heat and defrost to maximum. Consider changing altitude to find warmer air. If you suspect engine induction icing, you might need to adjust throttle and mixture, possibly applying carburetor heat if equipped, though not on the fuel-injected 172S, but maybe using alternate air, to find the setting that gives maximum RPM, indicating you've cleared the ice. You're actively manipulating systems based on your understanding of how ice affects them.
What about block static ports?
That's where knowing about the static source blockage and the existence and operation of the alternate static source valve is critical. If your airspeed, altimeter, and VSI start giving crazy readings, especially in IMC, switching to the alternate static source provides a backup, albeit potentially less accurate source of information, which could be life-saving.
And vacuum system failure.
If vacuum system failure, flagged by those LVAC or VACR enunciators, immediately tells you your attitude indicator and directional indicator are unreliable. This might necessitate transitioning to partial panel instrument flying, relying on the turn coordinator, airspeed, altimeter, VSI, and magnetic compass, a different scan and skill set, all prompted by understanding the vacuum system failure indications. Each of these emergency scenarios proves that system knowledge isn't just academic, it's fundamental to safe recovery.
Absolutely critical. Before we wrap this deep dive up, we can't talk about airplane systems without mentioning how everything literally adds up weight and balance.
Right.
Why is this so crucial, and what does the POH emphasize here? It seems foundational.
You said it, foundational. Correct weight and balance are absolutely fundamental to the safe operation of all the systems we've discussed. It impacts everything from performance to stability and control characteristics, and ensuring the aircraft is properly loaded is 100% the pilot's responsibility.
What are the key limits we need to know from the POH?
Your POH, specifically Section 6 usually, details the categories and limits. The Cessna 170S is typically certified in the normal category, with a maximum takeoff and landing weight of 2,550 pounds and a slightly higher maximum ramp weight for taxiing of 2,558 pounds. It might also have limits for the utility category, which are lower and allow for limited aerobatic maneuvers, though not typically done in a standard 172S.
What about baggage?
Baggage also has specific limits. There might be a maximum weight allowed in baggage area 1, the main compartment, maybe 120 pounds, and a separate limit for area 2, an extended rear area, maybe 50 pounds. But here's the key. There's usually a combined maximum baggage weight that cannot be exceeded, regardless of the individual area limits. For instance, the combined max might be 120 pounds total. You can't just put 120 in area 1 and 50 in area 2.
Got it. Check the combined limit. Why is staying within these limits so important?
The importance lies in performance and controllability. Understanding terms like maximum useful load, which is the max weight of occupants, baggage, and usable fuel you can carry around 895 pounds for a normal category 172S. Wing loading, weight divided by wing area, about 14.7 pounds to carry F2P. And power loading, weight divided by horsepower, about 14.2 pounds AP, helps you predict how the aircraft will perform.
How does being overweight affect things?
An overloaded aircraft will have significantly degraded performance. Longer takeoff roll, slower climb rate, higher stall speed, reduced maneuverability, and a shorter range. It puts extra stress on every system. The engine works harder, the wings have to produce more lift, the landing gear takes a heavier impact. More critically, being outside the approved center of gravity CG range can make the aircraft unstable or difficult to control.
Center of gravity, the balance point. How do we calculate that?
The POH provides everything you need for calculation. Section 6 includes an airplane weighing form, sample loading problems graphs, and formulas for calculating the longitudinal center of gravity, CG, the balance point front to back, and often expressing it as a percentage of the mean aerodynamic chord, MAC.
MAC, what's that?
Mean aerodynamic chord is basically the average chord length, leading edge to trailing edge, of the wing. Calculating your CG position relative to the wing's MAC is how you determine if your loading is within the safe approved envelope. Your POH explicitly states it is the pilot's responsibility to perform these calculations and ensure proper loading before every flight.
So it's not just about total weight, but where that weight is placed.
Exactly. This isn't just a numbers game on paper. If the aircraft is loaded with the CG too far forward, it will be stable, but feel heavy on the controls, require more elevator input for rotation and flare, and might even run out of elevator authority during landing. If the CG is too far aft behind the limit, the aircraft becomes inherently unstable, very sensitive to pitch inputs, and extremely difficult or impossible to recover from a stall or spin. It directly affects the effectiveness of your flight controls, your stall characteristics, and your overall ability to safely fly the airplane, regardless of how well the other systems are working. Weight and balance is truly step one for a safe flight. So wrapping this up, what we've really explored today goes way beyond just, knowing the names of the parts in a Cessna 172S. It's about appreciating the engineering behind it. It's about understanding the critical interdependencies between all these systems, how the electrical system affects the flaps, how the exhaust affects cabin heat, how fuel management affects engine reliability.
Right, it's all connected.
And recognizing the critical procedures straight from the POH that keep you safe and efficient in the air. From the simple mechanical linkages of the flight controls all the way to the complex network of the electrical system, every single component plays a vital role. Your pilot's operating handbook, it truly is your primary source, your ultimate guide for mastering this aircraft. It helps turn that raw information into real, usable intuition.
Absolutely. We've covered a tremendous amount of ground today, really delving into the intricacies of the Skyhawk, thanks to Section 7 and related parts of the POH. But here's something for you, our listeners, to mull over until our next deep dive.
Okay.
Considering all the systems we've just unpacked, the engine, fuel, electrical, flight controls, those crucial safety systems, which single system may be one that's often taken for granted, do you think has the most unexpected or perhaps the most subtle, critical role in overall flight safety? Think beyond the obvious engine failure scenario. What's the unsung hero, or maybe the quiet saboteur if it's neglected, that really dictates the ultimate safety of your flight? Something to ponder.